During this module, we'll look at additional central tendency and dispersion statistics using the case study data as our example. We'll anchor our discussion of central tendency around the mean, which we've already looked at. The mean, or x bar, is simply the sum of measured values divided by the sample count, n. Sometimes it's called the average, sometimes it's called the arithmetic mean, or the expected value. Sometimes just x bar. If there's actually a population used, we usually use the notation mu instead of x bar. For sufficiently large samples, the x bar, the mean, approaches the population mean, mu. But x bar, or the mean, is not the only measure of central tendency. There are other ways of understanding how a particular dataset clumps together other than just the mean. The choice depends on the context and situation. If the data is skewed, the middle value, or median, may be used. If there are extreme values, a trimmed average may be preferred, without the largest and smallest values that otherwise dominate a mean. And there are some other central tendency measures that we'll go over in the following slides. The median is the centermost value when discrete data are rearranged in increasing order. It depends on how many data are in the set. If the total number of samples is odd, the median is the value of the centermost n plus 1 over 2 value. If n is even, the median is the average of the two centermost values, n over 2 and n over 2 plus 1. If we take a look at the length data from our TV bracket trial 1, the first thing we notice is that the data is not sorted, so we have to sort the data to calculate the median. After we sort it, that's the second column, we count down and we see that there's 11 total samples, which is odd. So by the n plus 1 over 2 rule, the median is the sixth value, which happens to be 9 in this case. That actually happens to be the same value as the mean. The median and mean don't have to be the same. The mode is another measure of central tendency. The mode is simply the most common value that occurs within a dataset. It's the value that occurs with the greatest frequency. The mode is actually a discrete value in the dataset, while the mean and median measure central tendency, but it may not be actual values from the dataset. Just like the median required an extra step of sorting the data, the mode requires extra steps of counting all of the possible unique values and then choosing the value that occurs the most frequently, the highest count. In this case, we're looking at the TV bracket length data again, but instead of just trial 1, we've compiled all trials 1 through 4. If we count these individual values up, the most common value is 8, so the mode is 8. When we refer to the mean in statistics, we're almost always talking about the arithmetic mean, which was previously presented. The arithmetic mean is the sum of values divided by the number of values. The sample geometric mean is the nth root of the product, not the sum, of each value in a dataset. We represent it here as GM, and we use the capital pi symbol to represent that product, just like we might use sigma for a sum. If we look at the bracket data, the length measurements shown here from the first trial, the geometric mean we can compute as the product to the nth root, 8.39. It's not the same as the arithmetic mean. The geometric mean is used for a set of numbers whose values are meant to be multiplied, or those that are exponential in nature, such as growth of a population or financial investment interest rates over time. The geometric mean can be understood in terms of geometry. The geometric mean of two numbers a and b, for example, is the length of one side of a square whose area is equal to the area of a rectangle with sides of length a and b. The geometric mean is one of the three classical Pythagorean means, together with the arithmetic mean and another one called the harmonic mean. Another measure of central tendency is the root mean square, or RMS. It's most often used in discrete signal analysis. It's simply computed as the square root of 1 over n times the sum of xi squared. Unlike the actual mean, which has x summed up, this has xi squared, and then to get it back into normal units, you take the square root, RMS. If we look at the length data from our TV bracket trial 1, we can see that we simply square the x and sum them up, divide by n, and take the square root, and we have an RMS of 9.54, different from the mean of 9. When it comes to looking at the variation of data, we've already looked at things like the min, the max, the range, and the standard deviation and variance. Here, the sample variance and standard deviation is shown. It's computed as the mean minus the actual value summed up after being squared and divided by n minus 1. The variance has s squared notation, and we typically use the standard deviation as the square root of that because it's back in the same units of the mean. The standard deviation sigma of the population is the square root of the variance, sigma squared. Note that this is similar but distinct from the sample standard deviation s and the variance s squared previously introduced. The difference is the divisor n instead of n minus 1 for the sample. Another measure of variation is called the coefficient of variation, CV. It's the sample standard deviation divided by the sample mean. In the case of the length data from our TV bracket, CV is 3.3, the standard deviation, over 9, the mean, or 0.37. Repeated tests provide separate data sets comprised of independent measurements of the same measured variable. These data can be combined to provide a better statistical estimate of a measured variable than are obtained from a single sampling. The TV bracket example, where we had 4 trials, is a good example. The important restriction we make here is that each test sample is drawn from the same population. If that's not true, a different statistical analysis may be required. Consider M repeated tests that provide M independent datasets of a measured variable x. Each test, denoted by subscript j, consists of n sub j repeated measurements. The pooled mean values combine sample mean values weighted by the number of measurements nj for each test relative to the total measurements. In our TV bracket example, all of the different repeated tests had 11 samples, but they could have had different numbers. We use the brackets here with x bar and use the equation shown at the top. Similarly, the pooled variance combines the sample variance for each test weighted by the degrees of freedom for that test, bracket sx squared. The degrees of freedom, nu sub j, is n sub j minus 1, and the pooled standard deviation is the square root of the pooled variance. The pooled standard deviation of the means, or pooled standard error, is computed by bracket s sub x bar is equal to the pooled standard deviation times the square root of the sum of j equals 1 to m of 1 over n sub j. A statistic used to test the significance of variation between the sample means is the mean square value, bracket s sub x squared sub b. That's equal to 1 over m minus 1 with the sum from j equals 1 to m of n sub j, the mean minus the pooled mean squared. We briefly mentioned the F statistic and T statistic. The F statistic tests the quality of the population means under a null hypothesis, and the T statistic compares equivalence between two mean values from repeated tests.